So let's continue in our quest to derive the formula for the cross product of the vector A with the vector B. So we now know that we want to find a vector which has modulus equal to this. This is the formula that we arrived at the end of the previous video for the area of the parallelogram produced by the vectors A and B. So if we say that we're going to call our cross product vector x1i plus x2j plus x3k. So these are the components that we're trying to find, x1, x2, and x3. Now, the next thing that we're going to use is the fact that we want this vector to be perpendicular to both the vector A and the vector B. Now, that means that if you dot product this vector with both the vector A and the vector B, it needs to give you 0. So the formula for the dot product with A is going to be x1a1 plus x2a2 plus x3a3. So we can now say we want that to equal 0. So there's a linear equation that we want x1, x2, and x3 to obey. In addition, the dot product formula for this vector with B is going to give us x1b1 plus x2b2 plus x3b3, and we can also say that we want that to equal 0. So we now have two linear equations that these components x1, x2, x3 need to obey if this vector is going to be perpendicular to both A and B. So this, with the requirement that we want this size or the modulus of this vector to equal this, is going to allow us to almost work out what this vector is going to be, and we'll do that now. So if you think about what the solutions to this set of two linear equations are going to be, well, they are going to be all the vectors x1i plus x2j plus x3k that are perpendicular to both the vector A and the vector B. So on here I have drawn that straight line on which all vectors that are perpendicular to A and B are going to lie. So we're going to get a set of solutions that are all on this straight line. Now, if you then want the modulus of that vector to equal this, that reduces the number of possibilities to 2. It reduces it to the set of possibilities of one vector that's going this way of size equal to this, and then the other vector that's going the opposite way with size equal to this. So by the time we've worked this all out, we're going to just have two possibilities, one that's pointing in this direction, and then the negative of that that's pointing in the opposite direction. So we'll do this now. So time for some algebra now. So let's take this first linear equation here and rewrite it so that we can write what x3 is in terms of x1 and x2. So doing that, we take this term and this term to the other side of the equation and then divide through by a3, and we get that x3 is equal to minus a1 over a3 x1 minus a2 over a3 x2. Now let's substitute this into the second linear equation here, and what that turns this second linear equation into is this here. So we've got x1b1 plus x2b2, but now we've substituted in for x3 this equation in terms of x1 and x2, which we got from the first linear equation. So we're now going to get minus a1 times b3 over a3 x1 minus a2 times b3 over a3 x2. And then what we want to do is rearrange this so that we can write x2 in terms of x1. So, simplifying this, we collect the terms with x2 in, which is this term and this term. So we've got x2 times, and then we want to get them over the same denominator, so we've multiplied this top and bottom by a3 to get b2a3, and then we've got minus a2b3 from here, and all of that over a3, and then we've taken the terms with x1 in onto the other side of the equation. Again, we've got them over the same denominator, so we've multiplied this b1 by a3 at the top and the bottom, so we've then got that this is a1 b3, and because we've taken it to the other side, the negative has gone to a positive, so we've got a1 b3 minus then b1 times a3, which has become a minus because it's been taken to the other side, and then all of that is over a3 times x1. Now, to write x2 in terms of a equation in terms of x1, we just need to divide through by this on the other side. The a3's cancel, and we then get that x2 is equal to a1 b3 minus b1 a3 all over b2 a3 minus a2 b3, all of that times x1, and then we'll substitute this back into this equation so that we will then have x3 in terms of x1 as well, and we'll then have a formula for what x2 and x3 is in terms of x1, and then that defines this set of solutions of all vectors along that one linear line. So now taking this formula for x2 in terms of x1 and substituting it in here, we will get a formula for x3 in terms of x1 as well. So what this gives us is that x3 is equal to minus a1 over a3 times x1 minus a2 over a3, and now we're substituting in for x2 this thing here. So a1 b3 minus b1 a3 all over b2 a3 minus a2 b3 all times x1. Now, let's pull out the x1 from here. So we've brought the x1 here, and then we want all of this over the same denominator. So we need to multiply top and bottom here by this thing here, b2a3 minus a2b3, which is what we've done here. So we've got minus a1 times this thing from here, so b2a3 minus a2b3, and then we've expanded the brackets here to get minus a2 a1 b3, and then plus, because the negative cancels with the negative, so plus a2b1 a3, and then it's all over the denominator a3 times b2 a3 minus a2 b3. Now simplifying this down, this term here will cancel with the term that we get from here. So if we multiply this out, a1 times a2 times b3, that will cancel with this. This is a1, a2, b3 as well. Here we have a negative. Here we have two negatives, which makes a positive. So this term will cancel with this term. So we only have to worry about this term and this term. Now you'll notice both of these terms are going to have an a3 in, so the a3's will cancel. And finally, we will be left with a2 times b1 here minus a1 times b2, which is what's left here after the a3 has cancelled. So we'll get a2b1 over a1b2 all over b2 a3 minus a2 b3. Remember, the a3 has cancelled, and we should have an x1 here. So we now have formulas for what both x2 and x3 are in terms of x1, and this defines that straight line set of vectors that are going to obey those two linear equations which say that the vector must be perpendicular to A and B. Now, we have been doing quite uncareful algebra here. We haven't been worrying about whether we can actually divide through by things. So for instance, at this point where we rearranged this equation to this equation and we divided through by a3, we didn't worry about whether the multiplicative inverse for a3 existed. Now what if a3 had been equal to 0? We wouldn't have actually been able to do that algebraic manipulation, so we were quite uncareful. We did quite naive algebra here. Don't worry about that for now. Let's just assume that everything we did here was valid, and that all of the multiplicative inverses that we needed existed. We'll get a formula for what these components must equal in that case, and then we'll show afterwards that it works regardless of whether the algebra that actually was used to concoct it was rigorous or not. So if you try and actually take account of all the special cases, you'll end up with a complete headache. It's better to just assume that all this naive algebra was safe, get the result, and then we'll show that the result was valid for all the cases where the algebra wasn't actually valid.